Our next speaker is Dave Hewett on computational wave propagation.
Thank you. So I'd like to start by thanking the organisers for giving me the opportunity to present at this fantastic meeting. I'm very excited about this because I think it's been set up beautifully so we had a lovely talk from Valeri, from Marcus yesterday, and from CJ Chapman here, talking about wave propagation, and it's really, I feel it set the scene beautifully for what I want to say. Now, I never had the privilege of meeting Joe, but I hope you'll see that his work has influenced what I do quite a lot. And I was introduced to his work by John Hockenden, and I'm very grateful to John for pointing me in the direction of his work, and it's, as I said, it's had a big influence on me. So, as Marcus mentioned yesterday, computational wave propagation is a big industry. It's very important. Keller's usually seen as being somebody who contributed to asymptotic theory of wave propagation. What I want to convince you of today is that his methods, his geometrical theory of diffraction, are having a big impact on the computational side as well, on numerical methods. And there's an interesting class of methods called hybrid numerical asymptotic methods, which are kind of changing the game in some sense for scattering problems. So let me tell you a bit more about that. So the setup is, I'm thinking about high-frequency wave propagation, and as Marcus said, there are many applications in acoustics, electromagnetism, elasticity, quantum mechanics, and the generic picture is that you have some incident wave coming maybe from the top left here, hitting a scatterer. I'm thinking about linear wave propagation here. And this one happens to be a scatterer where the region inside has got a different wave speed, so there's some refraction hitting this thing. And you get this complicated wave pattern, and you'd like to understand how can I predict what this pattern is, okay? Especially in the case when the wavelength is very small, okay? So here I've got maybe 10 or 20 wavelengths across the scatterer. In applications, you might have 100 or thousands of wavelengths, and it's very, very difficult to capture these oscillations numerically or asymptotically, okay? And you should be saying, oh no, it's not, it's easy. Because, I mean, high-frequency wave propagation in some sense is easy. Every day when we open our eyes, we're solving this complicated inverse problem, right, of finding out where all the other people in this room are, and it's high-frequency wave propagation. The wavelength of light is tiny compared to human length scale. And how do we do that? Well, it's because light travels in straight lines, okay, in the high-frequency regime. And this is an idea of a geometrical ray-based approximation, okay, so light rays go around the domain, bounce around according to the laws of refraction and reflection. And these ideas go back for centuries. So the law of refraction is often known as Snell's law. So Jacob mentioned this in his talk. But Descartes also worked on this. But in fact, it was known a long, long time before that, even before people knew about that light was a wave, to sort of Persian literature. And I don't know, it's even appeared in popular culture, in Pink Floyd's album cover. I don't know whether Joe was into Pink Floyd at all, but he would have approved of this picture for sure. Okay, so this idea of these ray tracing ideas, geometrical optics is the basic one. It's a deficient theory in that it doesn't capture all of the wave behavior. Okay, so it only computes incident, reflected, and refracted rays. So in particular, it incorrectly predicts zero field in shadow regions. So here's a picture of just a schematic of some rays coming in from the top left, and they're hitting a screen here, the black line. There's some blue rays are the incident ones, green ones are the reflected ones going up to the right, and then behind the screen there's a shadow, and geometrical optics says field is zero. Okay? Ultra high frequencies, that's a reasonable thing to say. But in practice, of course, the field isn't zero there, and the propagation of waves into shadow regions is called diffraction. And so here's just a sample plot of a solution of the Helmholtz equation. So this is time harmonic wave propagation, scalar wave propagation. I'm plotting the real part of the solution. And here k is the wave number, which is proportional to frequency. So high frequency means large k, and that corresponds to small wavelength. Now this isn't particularly small, but if I plotted a really high frequency picture, you wouldn't see anything interesting because it'd be so oscillatory you wouldn't be able to pick out the features. But here you can see there's a triangle and there's a circle. I've got Dirichlet boundary conditions, wave coming from the left, and behind here in the shadow region, the field is non-zero. Yeah, there's the waves that come round the corner, and similarly around in this shadow region. So this isn't covered by geometrical optics, but rigorous sort of mathematical treatments of this started to come in over 100 years ago with Sommerfeld and MacDonald, who provided the first rigorous analysis of edge diffraction. So that's the kind of exact solutions for half planes and wedges. So here's a half plane, if it went off to infinity. And the corner of this triangle here is a wedge. Okay, so they wrote down exact solutions. And this is fantastic pioneering work. And then the case of smooth boundaries, so kind of shadowing around the back of this circle, this was studied a little bit later, and in particular some important works that Valeri mentioned yesterday, Fock and Leontovich. There was also related work by Pekaris, which hasn't received as much attention, but still I think is important. And they were using sort of these asymptotic methods, this localization that Valeri was talking about, zooming in, okay, to study this tangent ray diffraction, the rays that hit this smooth corner and then come around. Okay. So this was kind of progressing. And so what was Joe's contribution? Well, as I understand it, Joe's contribution was to show how these ideas could all be brought together into a ray-based theory. Okay. So the idea is that you still have these ray fields going around, but you get new ray fields created by edges, corners, and tangent rays. And we call these diffracted rays. And so if those pictures I showed you before, whereas previously I just had this incident wave and a reflected wave, so in the GTD, you now have a new family of diffracted rays which emanate from this edge and penetrate into the shadow region. Okay. And Keller's GTD is a way to kind of piece together all of these local properties to solve a global scattering problem. And it provides accurate solutions in the high frequency regime. It's very flexible because it just relies on these local problems. And it's physically intuitive, right? We have this notion that waves travel in straight lines. So it's a fantastic theory. And I'm going to be, here we are, the third person to show a picture of this paper. This is the kind of classical paper, the review paper from '62. And I just wanted to, and there's the pictures I showed you before, that you've seen before about these edge rays and the creeping rays coming around the back of a smooth obstacle. I just wanted to highlight a couple of things that I think is really fantastic about Joe's papers, the ones that I've read on this wave propagation business, is that he was kind of so open to different ideas and really wanted to engage with different communities. So here we've got something about experimental confirmation of this theory. We've got something about mathematical justification. We've got something about applicability, different problems that you might be able to solve with it. And that's something that I think continued in other papers. And I want to recommend a couple of other papers to you if you're interested in this stuff. They're kind of Joe looking back on and reviewing progress in diffraction theory. And this first one is sort of from '85, IEEE paper. And it's kind of looking back on the GTD, and I love this first statement. The development of diffraction theory in the last 100 years is discussed from a personal viewpoint, with emphasis on the geometrical theory of diffraction. It outlines the defects of the theory. So John mentioned this about there are certain directions where this GTD breaks down, and he talks about how many of these defects have been remedied. And here's another paper, which was the Gibbs lecture that he gave. And it's just a beautifully easy paper to read because it just gives you intuition, gives you a feeling for what's going on with these problems. Okay, I will omit as much technical detail as possible. That's a great thing for a graduate student to see when you're looking through a paper, right? Yeah, okay. So of course, I'm talking to a room full of people who mostly think in this asymptotic way. If I have a large parameter k, I'm going to do an asymptotic expansion. And if my solution isn't accurate enough, what do? Well, I find a willing PhD student and I tell them to go to the next term in the expansion. And if that's not accurate enough, I find another one and go to the next term of the expansion, okay? But not everybody thinks like that, okay? And these approaches are not always the right thing to do because you might not be in an ultra-high frequency regime, okay? So let's take a step back. Say we're trying to solve this Helmholtz equation. There are different ways that we might do that. And there's a whole community of people, and Marcus gave us an insight into that yesterday, who are working on purely numerical methods for solving these problems, okay? So this is an elliptic PDE, and you can discretize it, for example, with finite elements, or here's a boundary element mesh for scattering by a paper aeroplane, or something more nefarious. And so that's kind of a good idea when k is small, so at low frequency, okay? And I've talked already about in the regime when k is large, we're very high frequency, and then we have these asymptotic methods. Okay, and these have pros and cons, right? So the left-hand side, the numerical methods, they're controllably accurate. That means that if I refine my mesh, I can increase the accuracy as far as possible, as far as my computer will allow me. But they become computationally infeasible at large k because I have to resolve all these oscillations. So the wave looks like this, so I need at least as many degrees of freedom as is required to get an accurate picture of this. So I need a very fine mesh at large frequency, high frequency. On the other side, the asymptotic methods, the computational cost is essentially independent of k because they're geometric methods. They just trace rays around and then solve ODEs along rays. Okay? But the problem is that they're only accurate in the limit as k tends to infinity. And you can say, well, yes, okay, I can just find higher order terms. And people like John Chapman make this look absolutely easy. But it's not easy. Okay? To solve real problems using these methods, it's hard. And some of the canonical problems are very hard to solve. And the other thing is, in practice, you're not generally in one of these two camps. Sometimes you're right in the middle. Okay? So what do you do when you're at a frequency where the numerical method is too expensive, asymptotic method is not accurate enough? And this is a generic problem in computational wave propagation. And I want to put forward this hybrid numerical asymptotic approach as an interesting approach. And this is the idea behind this theory, is to try and fuse the conventional numerical methods with high-frequency asymptotics to create algorithms that are accurate but also computationally feasible for all frequencies. Okay, that sounds great. How does it work in practice? Okay, let's say a bit more. So the finite element method or the boundary element method approximates you by a piecewise polynomial on a mesh. That's the standard approach. Okay. Asymptotic methods are completely different. So they take the solution and they say, okay, I know I'm looking for something oscillatory. So they tend to look for a sort of sum of WKB solutions, where here I've got WKB means I've got this oscillating factor, e to the I, k, phi j, and this is a sort of oscillating phase. Okay, and then I look for some slowly varying amplitude, which multiplies that to give me the oscillation. Okay, and in general, I'd need a sum of these terms to capture the different components: incident, reflected, diffracted. Okay, but they all have the same sort of idea. And you have to do some asymptotic matching to figure out how these amplitudes depend on each other. And the idea of H&A methods is quite simple. It's that we use this same viewpoint, but rather than trying to find these amplitudes analytically by hand or solving ODEs, we let the numerical method, the finite element method or the boundary element method, find those amplitudes for us. Okay, so we approximate them by piecewise polynomials. Okay, but the idea is that these guys are much, much easier to approximate than the whole thing. Okay, and the goal is to have controllable accuracy, but order 1 computational cost as k tends to infinity. Okay, and this is realizable in practice, as I'll show you for some problems. So a little bit of history. The basic idea goes back at least to the 70s, but has developed more rapidly in the last few decades. And it's interesting to note that Keller himself was an early proponent of these ideas. And as far as I know, he has the only paper on this in the finite element context. Most of the work that's been done has been in the boundary element context. And I've highlighted some people who I think are in the room in bold who have worked on these problems, but many other people too. And as I said, Keller was an early proponent. Now, why have so many people worked in the boundary element context? Well, the reason is that for boundary elements, you only need to know the asymptotic behavior on the boundary of the scatterer, and that's generally simpler than the asymptotic behavior in the domain. Of course, as Marcus was saying yesterday, there are other disadvantages of doing domain-based formulations like finite elements, because you have to deal with the behavior at infinity. Boundary element methods build that in automatically, so that's another attraction for us. And if you're interested, there's a nice review paper by Simon Chandler Wild, Ivan Graham, Steve Langdon, and Ewan Spence on this business in Acta Numerica, which is very comprehensive. Sort of gave the state of the art a few years ago, but since then we've made more progress. Okay. So here's Joe's paper on the boundary element solution, and it's exactly what I just said. So each basis function is the product of a smooth amplitude and an oscillatory phase factor, like the asymptotic solution. The phase factor is determined a priori, and the smooth amplitude is represented by high-order splines. Okay? And the number of unknowns necessary to give a given accuracy with this new basis is virtually independent of the wave number. Fantastic. So what's my interest in this? Well, so I'm part of an extended collaboration centered at University of Reading, developing these methods for non-smooth scatterers. So Joe's method was for a smooth scatterer, and I'm thinking about domains with corners. So for example, we've looked at scattering by convex and non-convex polygons, two-dimensional, three-dimensional screen problems, and working currently on transmission problems like this one I showed you before. Okay. And here, of course, you have the added complication that you have singularities in the solution at the corners, and you have to build those into your numerical method. Okay. So our aim is, we have a slightly different take on it to some groups in that we try and prove rigorous error bounds when we can. And interestingly, this has actually led to new rigorous results in the GTD, which is usually viewed as a formal theory, but we've been able to prove some things rigorously, which I'll give you a flavor of that. So let's take a simple problem, sound soft convex polygons. So I've got Helmholtz equation outside, incident wave coming from the top right, and I've got Dirichlet boundary condition U equals 0 on here. And the scattered field's got to be outgoing, satisfy the radiation condition at infinity. So the idea behind these boundary element methods is that you first use Green's representation theorem to write the solution as the incident wave plus the scattered wave, and the scattered wave is a sum of point sources all around the boundary, and the amplitude of those point sources is given by the unknown Cauchy data, which in this case is the normal derivative of the total field. Okay. And here's this. So this is the Hankel function, which is the fundamental solution for the Helmholtz equation in 2D. So then this tells you if I knew this normal derivative, I'd have a solution to the problem. How do I find this? Well, let's take the limit as we go to the boundary. Left-hand side is going to go to 0, so I'll get this boundary integral equation for this normal derivative. So this only involves quantities on the boundary. Now, if I could solve this guy, I'd be able to find the solution. So how does the asymptotics come in? Well, so if I look at the field, according to GTD, on a lit side, that's where the wave can actually see this thing, I have a contribution from the incident and reflected waves, and I have a diffracted term. Okay. And this diffracted term looks like e to the IKS times something. This is arc length. This is a wave propagating in one direction, and this is a wave propagating in the other direction. So I've just got waves going backwards and forwards along with this thing. Okay. And these A and B are called diffraction coefficients. If I'm on a shadow side, I have a similar thing, but I no longer have the incident and reflected wave. But waves can come round by diffraction, and they have the same phase, these two phase functions. But the asymptotic theory, if you really want to do this properly, you have to think about all the multiply diffracted waves, and this is very complicated. Okay. Now, our method takes all of those and puts them all together into one package. Okay. So here's the theorem that we can prove about the regularity. We can prove that this normal derivative is given by the geometrical optics bit, okay, which is what I already said, plus this GTD bit, same phases. The amplitudes now, we don't have formulas for them, but we do know their regularity. We know that they're analytic in the right half plane, and they've got certain singularities which correspond to the corner singularities in the PDE. And the singularities depend on the exterior angles. And this captures all of the multiply diffracted rays, all inside that package. Okay, I think I've got a few more minutes maybe. I think I started at 10 too, is that right? So what are we going to do? We're going to take this ansatz, and we're going to replace these amplitudes by piecewise polynomials. Yeah, we're not going to find them analytically, we'll find them by piecewise polynomials. So we build some meshes, and we use an HP approximation strategy, so we increase the polynomial degree while simultaneously refining the mesh. And we can prove rigorous error bounds. Okay? We can prove that the Galerkin error is bounded by an exponential factor e to the minus the p is the polynomial degree times some rate tau. And the point is this tau doesn't depend on the wave number. Okay? And this means that we can get a fixed accuracy of approximation with a number of degrees of freedom just growing logarithmically as k tends to infinity rather than linearly. But in practice, it's frequency independent. Let me show you some results that prove that. Here's exponential convergence as p tends to infinity. And the accuracy, this is the error on the left-hand side, the accuracy actually improves as the wave number increases. Okay? And this is not so surprising because we've got an approximation space which can capture these oscillations. Okay? So just very briefly, I've been looking at the moment about transmission problems, and here you have some really interesting asymptotics going on. You've now got waves bouncing around inside this structure, and you can't hope to find all of them. What we've done is we've just included just the primary diffracted waves into our approximation space. Okay? And here's the kind of punchline. This is what you get if you compare the geometrical optics approximation to this thing. That's basically all we've got in asymptotics for this transmission problem. And Tony Rawlins is going to be talking about related issues later on. This red curve is the error that we get from our hybrid method. So we get an order of magnitude improvement over the asymptotics. And then this blue curve is what you'd get from a conventional method. If I just took a fixed number of degrees of freedom, for low frequency, it would do very well. It would do better than our method. But as the frequency increases, you lose approximation completely because you're not resolving the waves. Okay. And just to highlight, so at the highest frequency I've shown here, our method uses just 0.3 degrees of freedom per wavelength, which is very, very efficient. And we could continue for higher wave numbers, but I haven't done that. So I just want to conclude and say high-frequency scattering is a very challenging problem, and there's lots of interesting work still to be done. The GTD is a very powerful asymptotic method, but it's influencing computational methods too. And there are many big open problems to do, both on the asymptotic side. So I've mentioned here the transmission wedge, which Tony's going to talk about later, quarter plane, an octant, which I know people here, Raphael Assier is working on. In the hybrid methods too, we've got to think about 3D problems, multiple scattering. John Ock will be very cross if I don't say about the inflection point problem, which is also another open problem. And complex rays, yeah. So there's lots and lots of interesting stuff going on. So thank you very much for your attention. And, yeah.
So for the penetrable polygon like that, so what's your ansatz then for the sort of surface waves that are propagating, because they're not e to the IKS because you've got two different wave numbers?
So yeah, so here's the ansatz that we're using. So we've got a geometrical optics term which we find by beam tracing. So there's a whole load of rays which bounce around inside. We compute those by beam tracing. Then each corner of the polygon generates a diffracted wave, and so we build all of those phases. So we have exterior ones at the exterior wave number, and we have interior ones at the interior wave number. And we include all of those in our approximation space. But we don't include the internal reflections of those. We could do, but that would just make the approximation space more complicated.
Okay, thanks very much.